Welcome to G Fun Facts Online. Today we are diving deep into a specific and revolutionary pivot in the world of quantum mechanics, a concept recently crystallized by researchers at the University of Technology, Sydney, known as inverse entanglement. This is the story of how physicists managed to flip the geometry of the future internet upside down, turning a technological dead end into a global superhighway. To understand why this is such a massive deal, we first need to look at the state of quantum communication as it existed from roughly 2016 until late 2025. For nearly a decade, the model for building a global quantum internet was dictated by a single, brutal constraint: gravity and the atmosphere. The goal of a quantum internet is to connect quantum computers and secure communications using entanglement. This is the phenomenon where two particles, usually photons, become inextricably linked so that changing the state of one instantly affects the other, regardless of distance. This allows for quantum key distribution, or QKD, which is theoretically unbreakable encryption. The problem is that photons are incredibly fragile. If you try to send a single entangled photon through a standard fiber optic cable on the ground, it will likely be absorbed or scattered within a few hundred kilometers. You cannot amplify the signal like you do with standard internet traffic because of the no-cloning theorem in quantum mechanics, which forbids copying a quantum state. So to span the globe, physicists look to space. In 2016, China launched the Mickey satellite, establishing the downlink model. This model was a one-way street, where the satellite acted as the source. The satellite, orbiting in the vacuum of space, would generate pairs of entangled photons and fire them down to ground stations on Earth. The physics of this worked beautifully, because the atmosphere is thickest near the ground and thins out as you go up. When a photon falls from space, it travels through 480 kilometers of vacuum, which is perfectly clear, and only hits the turbulent soup of the atmosphere in the last 10 to 20 kilometers. By the time the air distorts the beam, the photon is already nearly at the receiver. It was the path of least resistance. However, while the physics worked, the economics were a disaster. The downlink model created a massive bottleneck. It required putting the most complex, sensitive, and power-hungry equipment, the quantum source lasers, on a satellite. Satellites are limited by solar power, meaning the lasers could not be very bright or fast. If a component broke, you could not fix it. Worst of all, quantum tech advances monthly, but a satellite is stuck in orbit for a decade, becoming obsolete almost immediately. It became clear that to build a scalable internet, we needed to keep the expensive, heavy gear on the ground and just use satellites as mirrors. We needed to go up. We needed an uplink. But for years, the uplink, firing a laser from Earth to space, was considered impossible. When you fire a laser up, you are hitting the thickest, most turbulent air immediately, right at the source. This creates two problems. First is beam wander. Turbulent air pockets act like shifting lenses, bending the beam. A tiny wiggle at the ground source translates to missing the satellite by kilometers once the beam travels the full distance. The second problem is beam broadening. The atmosphere scatters the light, causing the laser spot to spread out so much that by the time it reaches the satellite, the tiny telescope in orbit only catches a microscopic fraction of the photons. The loss rates were calculated to be insurmountable. It was estimated that to get one entangled photon pair to survive the journey, you would need to fire trillions, requiring power levels that would melt the equipment. That was the consensus until late 2025, when Professor Simon Devitt and Professor Alexander Solntsev from the University of Technology, Sydney, published their breakthrough on inverse entanglement. They proved that the impossible link was actually just a rigorous engineering challenge that could be solved by leveraging the one advantage ground stations have over satellites, which is infinite resources. The inverse entanglement model shifts the paradigm by utilizing the national power grid. Unlike a battery-limited satellite, a ground station can plug into the wall. This allows them to crank up laser intensity to levels impossible in orbit, essentially brute forcing through the atmospheric attenuation. But power alone is not enough. You need precision. The UTS team integrated the concept of adaptive optics, a technology borrowed from astronomy. In this system, ground stations fire a bright orange sodium laser into the upper atmosphere alongside the quantum signal. This laser excites sodium atoms, creating a fake artificial star. Sensors on the ground watch how this fake star wiggles in the turbulence. A computer calculates the inverse of that wiggle and applies it to a deformable mirror 2,000 times a second. The quantum laser bounces off this rubber-like mirror and enters the atmosphere pre-corrected. It effectively cancels out the atmospheric distortion, allowing the beam to slice through the air like a needle. This technological shift allows for the most critical component of the new network, the dumb satellite. In the inverse model, the satellite does not need to generate quantum states. It effectively becomes a flying mirror or a simple receiver. The protocol works through a process called entanglement swapping. Here is how it works. Ground station A, let us call it Alice, generates an entangled pair. She keeps one photon and fires the other up to the satellite. Hundreds of kilometers away, Ground Station B, or Bob, does the same. The satellite receives one photon from Alice and one from Bob. It performs a joint measurement on them. Due to the strange laws of quantum mechanics, this measurement swaps the entanglement. Suddenly, the photon Alice kept on the ground and the photon Bob kept on the ground become entangled with each other, even though they never met. The satellite was just a middleman. This transition from downlink to uplink creates a democratization of access. In the old model, if a company wanted a quantum network, they had to launch a billion-dollar laboratory into orbit. In the inverse era, the satellite infrastructure becomes shared, generic, and cheap. Telecommunications companies can launch constellations of cheap, shoebox-sized CubeSats that act as simple receivers. Then, any user on Earth, be it a bank, a university, or a government, can buy a ground terminal and point it at the sky. The complexity stays with the user, where it is accessible and upgradable. Professor Devitt compared this to the electricity grid. We do not generate electricity inside our laptops. We generate it at massive power plants and transmit it. Inverse entanglement turns entanglement into a utility. The ground station is the power plant, generating the quantum fuel and pumping it into the network. This also solves the bandwidth problem needed to connect quantum computers. To link two quantum computers to create a distributed supermachine, you need millions of entangled pairs per second. Downlink satellites are too weak to generate that. Uplink stations, powered by the grid, can generate that massive bandwidth. This enables applications like blind quantum computing. Imagine a hospital that wants to use a cloud quantum computer to simulate a new drug, but cannot share the sensitive patient data. Using the high-bandwidth uplink, the hospital can entangle their local system with the cloud server. They can then send instructions encrypted by the laws of physics. The server performs the calculation without ever knowing what the calculation is or seeing the raw data, returning a result that only the hospital can decrypt. The roadmap to this future relies on three key technologies. We have already discussed adaptive optics. The second is synchronization. For the satellite to swap entanglement, the photons from Alice and Bob must arrive at the satellite detector at exactly the same instant. Since the satellite is moving at 27,000 kilometers per hour, the ground stations must use predictive timing, firing their photons early or late based on the satellite's position to ensure they collide at the perfect nanosecond. The third technology, arriving in the near future, is quantum memory. Eventually, satellites will carry crystal storage devices that can catch Alice's photon, hold it for a millisecond, and wait for Bob's photon, relaxing the extreme timing requirements. We are now moving toward a hybrid quantum network. Layer 1 will be fiber optic cables for short distances within cities. Layer 2 will be the inverse link, connecting those cities to the orbital network. And Layer 3 will be the orbital mesh, satellites talking to satellites via laser to route traffic globally. The announcement by UTS is comparable to the switch from dial-up to broadband. It transforms the sky from a barrier into a bridge. By reversing the direction of the stream, putting the power on the ground and the mirrors in the sky, the quantum internet changes from a scientific curiosity into a rugged, industrial utility. The future of the internet will indeed be written in the language of quantum mechanics, and thanks to inverse entanglement, that future is finally scalable.